Okay. So, Vishal, tell us about yourself. What's your background? What have you been doing? What's your interest? And yeah, what else do we need to know?
Okay, so I'm right now the co-founder and CEO of Imbold. We build. So my passion is good software products, and that's also my problem because the amount of I like using good products of good quality, especially software products. And off late, the last 10, 15 years, even though software has taken over our lives, I'm just appalled at the quality of software and how careless people have become. And that's what um, is my mission. I always have this saying that software is going to be in our bodies in 5 years, and you don't want it to crash as often as your smartphone does. So that's
Okay.
what keeps me alive, and that's what motivates me to build solutions, tools, and basically work with the community to help them, write good software so that everyone's life is peaceful.
Okay. So basically, quality is a huge topic, right? I mean, that's like, I don't know, it goes all over the place, and perhaps you will talk also a little bit about some aspects of that. Is
Right.
it you're focused on, I suppose, given the topic of the track, for you it's mostly web development and JavaScript web development, or is it also backend, or what is sort of the scope of the that you're looking
Everything.
at? Okay.
Actually, my background comes from the real-time embedded world. So
Okay. Okay.
I'm a C++ guy. So it is everything. I used to
Okay.
be. I pretend to be now. I've been, but yeah, that's my background. I cover everything from the metal to the web.
Okay. Cool. Yeah, interesting. Then we have a broad spectrum of questions, I guess, that we can ask, because then we can go all in on that whole topic there.
Yeah, no
Okay.
problem.
Then I would propose I will queue up the stream here, the pre-recorded talk, and let's see if this works out. And then if it works and it starts streaming, I'll remove us from the stream for a moment, and then we will be back after the pre-recorded talk. And so everybody, sharpen your pencils, write down your questions or write them in the chat, and we'll be back with you after the talk.
Today, we're going to talk about the future of static code analysis and how applying deep learning is going to transform software development. Let me start by stating what we think is the state of software today. I think it's a well-known fact that software has eaten the world, but today the problem is bugs are eating software. And as a consequence of that, software development has become an extremely inefficient process. By inefficiency, I imply the output per dollar per intelligent human capital spent. If we could make this intelligent task more efficient, I think that could transform the way things and products could be built in the future. Why now is the opportunity? And the reason is today we are almost living in the world of collective intelligence in the world of software. Let me explain why and how. There are mega knowledge and data sources that are arising today. Open source software is well known. Then there are social software platforms like GitHub, Stack Overflow, Quora, Google. The infrastructure has completely been commoditized, the AWS, the Azures of the world. IoT is going to increase this data source by leaps and bounds never seen before. And of course, there are tools like Atlassian, Imbold, AppDynamics, and these tools are really driving this opportunity of harnessing these massive data sources. And therefore, what I see today is almost we are standing at a cusp of computing history once again. And let me explain what this means. I think when software development really started scaling up, and we go back to 1960, we started building software. And as a consequence, there were lots of added data sources that started getting created. For example, issues, logs, requirements, diagnostic data. From 1960 to 2020, what has happened today is thanks to big data, computing efficiency, a lot of that data has now, we have started making sense and intelligence out of that. Things like correlation engines, prioritization, ranking, deep learning. And I think the next leap and the next change that's going to happen is not going to take us 60 years. It's going to take us probably 10, where we're going to take all this collective intelligence that's being created today and deploy it to actually mass usage. And what we think one industry which is completely underrated today that's going to be impacted positively by this is software development and static analysis specifically. So let me quickly share that why this is happening. It's not science fiction anymore. There are companies like Facebook who have already started using deep learning through their products internally called SapFix, for example, and also the open source community in the Linux Foundation, where they are experimenting with building stable trees using machine learning. So it is slowly getting pervasive in terms of machine learning and software development and code analysis. So let me quickly recap what is conventional code analysis, or what is conventional static analysis, and what it can do. A conventional static analysis is essentially a rules engine that is written for certain behaviors in software that need to be detected, which shouldn't happen. And the way this is done is you have experts / experienced developers who come across a bug or an issue. They write a rule, and the rule goes into the search engine, or the rules goes into the static analysis engine, and you check your code against it. This is the conventional approach, and this is how tools being offered in the market today offer static analysis, which is good, but it has its limitations. A classic limitation is a bug that I'm showing you today. If there was a memory leak that was found during testing and it was fixed, this perhaps would not, if it had escaped the testing process statically, it might have been difficult to find it. And the challenge is the occurrence of these rules happen in different environments. Sometimes you can catch it through static analysis, sometimes you don't. And often if it passes static analysis, you find this bug in testing, in functional testing or manual testing. But then what happens? The knowledge is lost. You cannot be writing rules for every bug you find during testing, which has passed static analysis. So that's the limitation that we see. Taking that forward, if you look at this Venn diagram and we see how does classical testing and static analysis testing differ, and what is the overlapping area? Bugs found during classical testing are usually related to business logic or standard conventional bugs related to UI. Static analysis bugs are found, usually detect non-functional bugs that you can find statically. But there is a slight overlap between conventional testing and static analysis testing, which are things like exceptional handling. What I'm trying to say here is there are certain bugs which you can find through static analysis, but which is not often found during the static analysis process and found later in the testing cycle. And the challenge is if you have more and more of these issues which are pushed to being found in testing, which are not found or which cannot be found by the conventional static analysis rule, the process becomes very efficient. And this is where you start looking at very interesting use cases where machine learning and deep learning can be leveraged. Now I'll go back to what I had spoken earlier about these massive data sources, right? Today, a piece of software or a line of code is no longer living in isolation. Today, every piece of software has a certain family of data assets around it. And these data assets could be the requirement for which the software is being written. So that is usually in systems like Jira from Atlassian. And the source code is stored in repositories like Git, Bitbucket, or whatever have you. So there are information sources that are trickling down, which are related to the line of code, which are gone beyond that piece of software. And we have a relationship behind it. So if you look at this diagram that I'm sharing with you, you have a commit of your software. A commit consists of a code change And I'm taking, and let me just quickly explain what happens in a commit, and I'll generalize it. Every commit that is made in software either is a new feature that has been developed or a bug that has been reported and is being closed or being fixed. These are the two essential commit characteristics you have in software. And so I'm now in terms of applying deep learning to static analysis. Let's look at those commits which have been used to fix bugs. So essentially what is happening is you have a commit. A commit contains a particular code change which has been made to either fix a bug. So I'm a developer, someone reported a bug against my code, I fix it, or I make a commit and it introduces a bug which is found in testing. But conventional static analysis tools do not have any relationship, or they don't offer a relationship between the code changes and the bugs reported. And that is an interesting use case which can be leveraged by techniques like machine learning to build a knowledge graph, which can then be used to ensure that bugs are not mistaken. Let me take that further. You can now with all these different knowledge banks like Jira, GitHub, Embold, you can now correlate any changes that have been made in your repository and correlate that change to what, and I'm talking about bugs, what kind of bugs did that change report? So did it report a bug related to the design of the code or code quality? If you can learn from that, you could start building a very interesting knowledge base about changes which can be used. And I'll probably try and simplify that for you. So assuming you made a commit and the commit created an issue, it could be a design issue found by tools like Embold, say assuming it was a God class, and then I fix that. So what you could do is you could use neural networks to learn what changes in code create a certain issue type and what changes in code close the issue type. And that difference can be learned by a learning engine. And that is, I think, the genesis of a very, very powerful application of deep neural networks that will transform the whole learning process in code analysis. I was reading somewhere that 70% of bugs that occur or happen in software in the open source world has happened in the past and someone's fixed it. Usually these bugs are related to synchronization, memory leaks. And if there was a way of learning from the mistakes of these past bugs using machine learning, so for example, what changes in code created these issues, and those changes were fed back to development teams today to ensure the past mistakes are not made, in theory, you could prevent those 70% bugs coming in projects. It's just like I have a team and the team changes hands, new developers come in, and they make the same mistakes again in the code, which often happens. We've heard from large engineering organizations that up to 40% of issues that come up have come in the past and someone's fixed it. So using this simple architecture, if this past mistake learning can be harvested based on this simple diagram and fed back to developers today so that they didn't make the same mistake, you could get massive efficiency. Let me start that with an example. So what you see here is your Git repository. As you can see, these are my commit IDs, these are my commit details. And I was just taking that with an example that we have seen. So assuming a neural network has been trained on a repository. Here are my commit IDs. It has also been trained on which commits from your issue system. So this is Kafka, and you can do that. You can just pick up any neural network and you can run this experiment as well. And what I've seen here is, the model has been created. If you saw my diagram, the model creation has happened. It took me a couple of hours to build the model based on Kafka, GitHub, and Jira. And here, proactively, my model flags this commit, which has, in this there are 12 chain files. It has flagged two potential issues. What this means is, it has found two issues in the code which resembles issues made in the past, and also shows you how it was fixed. So here it says, another client assigned new task. It says it has found this matching a similar commit that had happened in the past that had created a Jira issue. And for this example, I'll show you it's created a Jira issue, which is Kafka 6054. I click on it, I go to my Jira. So this is the bug that had happened in the past, which the model finds that I'm trying to create this again. And the model has also learned from Jira that this bug that had come here had created a concurrency and a memory issue. And it says maybe instead of task ID, you should use a new array list, and you could potentially prevent this bug. And this is what I meant. This is Kafka, where in the open source world, people are documenting bugs very well. People are documenting error messages, and you can take all that data and harvest it. And this is what I meant when I said these massive data sources are arising from which you can learn. I mean, you could extend this further and say this issue that it's almost like Minority Report for coding, because it's flagging issues based on past learnings and preventing me from missing it. So it's telling me, Vishal, you're about to create an issue which resembles a past issue, but I could train this model further and could even tell me, by the way, you could talk to Matthias or James Cheng, and they could perhaps guide you or share their experience with you. So at the back, what I think will happen, neural networks will also build this massive knowledge graph, a knowledge network of open source developers, bring them together. And that itself could be so powerful, because today you have no means of using that besides plain natural language text. So maybe there's someone out there who could build a more sophisticated version of Stack Overflow, which is not just a bunch of strings and text, but also has source code, GitHub repositories, intelligence from that, which can be mined and used. So this is an example of how you could use, how neural networks are going to change based on these massive data sources that are being created. Okay, so that was an example that I showed you on Kafka. And what I've done is, it's really fun. You can just build a neural network and train it on open source data sources. So here's another one that we ran it on CloudStack, large data sources, lots of commits, very popular. And this is the development history, as you can see, and it has predicted a bunch of issues. There's one thing I would like to say. If you read some of the papers that is coming out of Facebook research, there will initially be a question on how accurate is the forecast. And I think, as with any neural network based prediction, in the beginning, data shows that it's going to be it's not going to be accurate all the time. So we have to be, neural network based prediction is not 100% in the beginning. It's just like learning. But with powerful feedback mechanisms, with powerful fine tuning, you can start increasing the accuracy, and as with any learning engine. So in large organizations which are experimenting with neural networks and source code prediction, if you can get up to a 50% accuracy in terms of prediction of bugs, and what that means is, if 1 out of 2 recommendations that the neural network based model recommends works, you're doing very well. Because of course, there will be some vague issues which the neural network has learned which may not have relevance. So we assume in the first generation of neural network based recommendation engines in static analysis, you will have lower accuracy. But this is going to get better and better as new algorithms come in, as transfer learning comes in. This will only get better. Looking at this example of CloudStack, let's see. This commit history, it says it sees 10 potential issues. So if you go down to this and see what happens, and it says, okay, this one is it looks similar, but yeah, this is an example of what I say. The recommendation is interesting, but maybe not as exciting. So maybe I'll probably take an example of another one where we see this is more of diagnostics that's coming in from the logs. So it's saying instead of diagnostics, use the other use command install conf because otherwise you could create an issue. This looks interesting, but this may not necessarily be as exciting as I think. So yeah, this kind of validates what I'm saying. Sometimes the recommendations may not be the most interesting one. Here's another one that I see. Is formatting the class. It was a mess. See, so the learnings can be funny too, because someone in the issue system actually said this was, just get the formatting right, otherwise you'll create an issue. Yeah, there's another one, and this is interesting. So he's saying if this change that you're writing here could potentially lead to a security issue. And so what is its recommendation is here is, it's in the throw block, but you could just drop the null here, and you could have someone, a malicious user is able to get the size of the cloud by enumerating the ID. So you are actually creating a security issue. And the point to note here is that no rules need to be written anymore. So you're entering the realm of ruleless static analysis engines based on machine learning, and the issues that sometimes these can find are completely catch you off guard. It's another example that we show where there could be some invalid recommendations, and the model only gets better. So this was just a quick analysis, and this needs fine tuning. But just the example is to show you how neural networks can be used to learn from these massive data sources like GitHub, Jira, Bitbucket, and literally convert all those knowledge banks, all those commit histories, all the issue logs into security analysis tools. So let's look at this diagram. So this diagram explains what I've been trying to show with the previous slide. So you have commits. The commits created an issue which is recorded in Jira. And now you could, then you fix the issue. So something's changed. So this was assuming the buggy piece of code which has been fixed. And then you have fixed this, and then you can see what changes in the code created this fix. And you have the issue description, which is coming from your repository. And then based on that, you can use to train a neural network and predict, and you can almost predict the bugs and the relevant fix to the bugs. So what happens is when you have new code being made, you can do a sequence match of a code pattern that resembles a past bug, and then you flag it as a likely bug, and you also have a recommendation because you've learned how similar bugs have been fixed in the past. So there have been certain experiments that have been done by companies around, and they've found that this technique works really well. And there's very simple testing. You can test it in a very simple manner, the accuracy of your model. What you could do is you could take a code base, say has 100,000 commits. So let's take large code bases like Linux or Chrome or whatever. And you take 80,000 of the past commits to train the model and predict bugs, and then see actual bugs that have occurred in the repository. So it's very easy, right? So assuming you take 10 years of data to train the model, you have a project which is 10 years. You take the first 8 years to predict and learn, and you predict bugs which you can correlate to bugs which you actually have in the following 2 years. So take the past data to learn and predict bugs, and use the last 2 years to see if the bugs predicted actually reflect the bug that have been reported, and that's how you can train the model and fine tune it. So it's very easy to apply this. You can do it by yourself. There are all the learning techniques are available, and we think this is a very powerful technique of applying past learnings. Today, you can apply classical deep learning to learn from one repository. However, there are some challenges when you want to train your model on multiple repositories. So there are research happening using techniques like transfer learning. And once that technique of transfer learning is fine-tuned and it works, then in theory, this model that you have can be used to learn from every repository on the planet. So imagine if you could have a model which could learn all the bugs that have ever been made in the open source world, all the different changes in the code which has been able to fix it, and all possible popular programming languages, you could essentially have the most powerful static analysis engine on the planet. So imagine if we could transform the commit history, the issues history of all the repositories available on the planet. And I say the first case is open source. You could literally transform that into static analysis. Why? Because static analysis rules are essentially bugs that you shouldn't have in your code, non-functional bugs. And these bugs are reported through experience. Where does the experience come from? From the open source world. So today it's done manually, it's done by small teams, it's done by people, it's not scalable. But applying this schematic and technique, you could literally train your model on virtually infinite amount of repositories. And I think that is what is the most exciting development you will see in the next 1 or 2 years that's happening. And from our record, there will be solutions like this, or there are solutions like this, or static analysis engines like this in the market. They're probably language specific. This is going to be one of the most exciting changes in the world of software development that's going to come in the future. And what is going to be the outcome? Because things like missing conditional checks, alternative API recommendations, missing function calls, these are going to be examples of bugs that can be learned based on a repository and fed back, because you technically cannot write a rule for all repository. And there are certain limitations, of course, for any neural network. I think this approach is not going to work if there's not enough data. So if you have repositories with less than 3,000 or 4,000 commits, I think there won't be enough information. But on larger systems like Kafka, Linux, Hadoop, Chrome, Windows, Excel, this is going to be very, very powerful. And I think this change that is coming, will result in an acceleration of software development velocity by orders of magnitude never seen before. So carpe diem and experiment with this, and happy to take questions.
Excellent. Okay. So thank you very much for your talk. It was very interesting, the topic. We already gathered up a bunch of questions from the public here. A bunch of those already overlapped with some of the questions that I had. Maybe just to dive right into it, one thing that I had here in my questions regarding what you talked about with AI and static code analysis is, and you went into this a little bit at the end of the talk as well, as how much data do you need for this to be working correctly? You mentioned the amount of commits, sort of. Is that how I should think about this? What is sort of the important metric there?
Yes. So what we've seen, what I've seen is, if you have less than, at least for the technology that we work on or we experiment with, anything less than 3,000 to 4,000 commits, and the learning is not very powerful. But then after that, it gets really, really interesting. So we recently, we're doing some fun stuff on the Chrome database. It's over 100,000 commits.
Right.
And it's fascinating. And it takes a lot of time for learning. It can take at least 2 days because we don't, we run it on our local infrastructure. We don't want to use a lot of cloud costs. That's quite expensive for training. But it's interesting. Linux, Chrome, these are very interesting examples.
Okay, cool. I mean, maybe fitting to that question is also coming from Carlo, who asked in the chat, is this language specific or language agnostic? So how much, to what extent is this linked to the specific programming language or even natural language for the messages?
So I think right now it is, I would say, language specific, because you still need language specific AST parsers. You can have generic parsers, but then it's generic. So the true learning is when you have language specific generic parsers, then it becomes very accurate. So from what we are doing, we experiment a lot. We've got great success with C++, which is the toughest bit, and Java and TypeScript. And now, it's not, as developers, we always want to go after the toughest beast. And so we went after Java. And it was interesting for C++ because in C and C++, sometimes all your historical, you don't get all the information about your code in your repository. You can only get it in build time, right? Because so that's where we've had to use some interesting techniques to learn, because you have to learn from everything that happens in the past, every chain that was made, every function, every attribute was connected at the AST level, and you don't get that information through repository for C++. Therefore, it was a tough one. But for other things, everything is in the repository. The learning is pretty standard.
Okay. Cool. I mean, the approach that sounds really exciting. I think many of us have experience with rule-based approaches. So you've talked in your talk about different kinds of static code analysis, and I mean things like ESLint, for example, in the JavaScript world, or in TypeScript, you have SonarQube doing static analysis in the backend using some kinds of rules, and I don't think they use AI, at least as far as I know, to any extent there. So it's interesting to see like these new things sort of entering. And what I especially like is this, that you tying in the commits and the Jira issues, because that's information is usually ignored, right, completely. So this feedback, and it's such important information. Like if you're debugging a problem, you're looking into the Git history, you're looking at what was the commit message, what issues did somebody have already before that. Does that make, does the linking to the issue tracker, to what extent does that influence the quality of the results? Like, is there a does there have to be like a very strong correlation between your commits and your issue tracker, or?
In theory, yes, we would. I think every modern organization, open source world, they have very solid documentation,
Yeah.
and that's what Linus says, right? He's saying you should do service to your future developers by writing what the commit is all about. So we can
Yeah.
learn. I mean, you can learn from Jira, you can learn from even now Git commit. They have very good messages, and interestingly, so we are excited. We are building this graph, and it's crazy. Today, it's just Jira, but we are extending it to from your build system, from your testing data, from your ops. So you can even pull data from App Dynamics or data or your Splunk and bring it all together, because the more information sources you can feed your AI, the predictions can be crazy. We've had experiences where AI just pops up and says your incorrect usage of API, and we're like, come on. But it was right. It kind of figured it out. So it is interesting how this is going to go, and that's what is very exciting.
And when you get a model like this up and running, maybe using your software, using something similar, is it possible to do like incremental updates? Like you mentioned that in the beginning you need like a lot of training, and it's for the whole data to come together. But after that, you have some sort of operational phase, right, where you're basically doing new commits, you're creating new bugs, new code. The system can sort of deal with those incremental updates.
Yeah. So it depends on what your organization, what your team's philosophy is. So you can say update the model in theory with every commit in the night, every master commit, or update it every week.
Okay.
Just like, and it's interesting, IntelliSense, you probably heard of IntelliSense or Microsoft. So they also have something similar, but they have it outward. So they train their model on open source, massive Git repos, and they feed it to you. But we are completely the opposite. We train from the internal repo, because we think that has more value for a team, from a simple reason that you do not want to make the same mistakes of the past. That's such a irritating problem, but it just bugs the shit out of me when I see this and I say, man, this was done. Go look at that, or talk to John, or talk to Anna. So I think we're trying to solve our irritation, and interestingly, we find that resonates a lot with a lot of teams.
I think that's an interesting point, because we spent, like, I'm in a development organization as well, and we spend a lot of time talking about what went wrong. What can we do better in the future? Can we please all think about that? And what's frustrating always to me is to sort of have in a meeting like, okay, people, can we talk about X, Y, and Z again? In general, we shouldn't do this because blah, and we learned this, and then not everybody is there and nobody remembers it anyway. And so it means solving that would be, or at least solving a little bit of that problem, like, can we just in this institutional knowledge, right? That's not like completely widely spread, to sort of at least have a little bit of that automatically at our fingertips would be very, very interesting, I think.
Exactly. You read our use case for that. We think, damn it, learn from the past and solve that first.
Yeah. I have related to that a question from Johannes, who asked whether does it make a difference if like repositories often have different conventions? How do they squash commits or not? Maybe how do they classify the issues? Like, is it a bug or a feature or something? The commit messages may be different. Does that make a huge difference, or?
Yeah, I mean, it doesn't, but it's a good point, because at the core, it's still very simple, right? We look at AST diffs and we look at issues, so it doesn't matter. But I remember there was one interesting, I can't take the name of the customer, it's a very large embedded, one of the largest chip manufacturers. And when they were experimenting with our model, the model learned nothing. And we were like, shocked. And what the hell happened? And we found out that they didn't call issues. They called issues insights. And because the model so there was no learning, there was no issues. So yeah, some of those nuances you got to, but that's a configuration. Now there's a configurator, you can say, okay, if it is insight, it is issues. If it is this issue, so you can do that. But yeah, we have these quirks
Okay.
But it's just, yeah.
That's really funny. I like that to rename the bug tracker or the issue tracker to the insight tracker. That's something we should think about for our work as well.
Yeah,
That's not bad.
we were politically correct. So we were really, it was massive repositories, like almost like 40,000 commits. This software is running on 6 billion devices. How can it not have issues? And we see it. And then there was a small tweak, but that was, we learned.
But I mean, that company you mentioned sounds like a really big company. There was a question from Andoni in the chat who asked, like, from what kind of size of company do you think you get some sort of return on investment for this kind of system? Do you have a feeling?
I think it depends on the code, on the commits. It doesn't depend on the size. Usually, if you have small teams and the teams have been around together, you don't need our tool because, hey, I know you, I know what you did. But it starts getting interesting when you have distributed teams. So you have people you don't know their programming style. You're not living in the same room. You can just plug it on into your, it's very simple setup. Just set up a Docker instance as an add-on, point it to your and the learning starts. Usually the first learning, like in Kafka, right? We are plugged into Kafka open source. So we keep an eye on. It took up the base learning was 2 hours and then it's incremental. Then it just
for the whole of Kafka. Okay.
Yeah, it's quite fast.
Okay, cool. Yeah. There was a question from Carlo as well in the chat that I've seen. One question that he had was, what system you use for graph processing? So I think the assumption is there is some.
Yeah. So we pass. I think we think just by this approach you will not get good results. We also work with a static analysis tool. So it's rules based and machine based. For the graph, we experiment with Neo4j, but now we are moving to migrate onto something else because we're not happy with the performance. That answers the question. But we do build a graph. We build the whole AST knowledge graph. That's why we know everything about the code. And you can imagine knowledge graph for one version. So imagine 2 million lines of code and then 35 releases. That's a lot. Yeah.
And so are you willing to disclose what you're moving to, or is it secret what you're moving to? That's more performant than Neo4j?
No, I think we are experimenting with it, and I think we will come up with a solution. We're also looking at changing our architecture to move toward more time series databases as well, because it's a fundamental change. Right now, we have a core static analysis, which is really powerful, which looks at design issues. So it's probably imagine that like a next generation of SonarQube. But this we've built the first stack, and now we are looking at of completely upgrading it. Maybe in the next event, I will be able to share more on how we migrated from our conventional stack to a more modern stack.
Okay. Yeah, well, I think that still the stack you have is quite impressive. Carlo has a follow-up. Actually, he's asking if you have experience with the Redis graph. Apparently, there's something from Redis.
We haven't experienced that, but we've analyzed some code for Dell for Redis VMware team.
Okay.
Yeah, that was interesting. But we do sometimes talk and collaborate with large organizations and big open sources because they're very curious, right? Because they are the ideal candidate, and our platform. I mean, it's free for open source. So if any of you open source guys, talk to us, we'll give you the platform, plug it in, and learn. Yeah. Cool. It's not open source, but it's free for open source. So set it up and run with it in your CI/CD if you're experimenting with it. No problem.
That's really interesting. That could be a really good start. I think many open source projects could benefit from this kind of thing. That could be really interesting. I mean, there's a question also from Carlo on this, on how to use it. Is there a trial version, like to try it out? Is there a way to try out a system on a code base and then see what it brings?
Yeah, absolutely. So right now, I think the neural network is Java and C++. So if it is, and we would say anything over 3,000 commits and gets interesting. But as I said, caveat, we have massive discussions sometimes with people who are really into it, like the Facebook's verification team. And interesting, we read their papers, we discuss sometimes, also a larger community. And that's what I said, take it with a pinch of salt. It's funny, it will not, all recommendations are not serious. And we are building a feedback mechanism, but there's a discipline. Some developers can be pretty naughty and they could just misguide the learning engine.
Right,
So that's a bit, I mean, you can do that, but we have to build a bit of an organization discipline for companies to use it. But yeah, I mean, we can absolutely offer it to anyone who wants to plug it in and use it. We are actually looking for feedback. So yeah, happy to do that.
And you mean that there's like a feedback system already in the system? Like if I see that the system has identified something and I'm saying like, nah, that's not really an issue, could you give that feedback and then say like, click and that it learned from that it incorporates.
So we did that. We pulled that feature out. We did it very simple, like thumbs up, thumbs down, and it went haywire. It completely misguided the system. Our developers broke it first. They had fun.
Okay.
So we're thinking of a way to. So we pulled out that feature. So right now there's no feedback. But you should know your system. So you should be able to judge. Hey, I know this code. This is that issue, and I might ignore it. But just to alert people and start leveraging their knowledge, I think is useful.
And you mean that the system went haywire was basically people misusing the feedback system? So basically, if you would have some, I don't know, maybe a review process or something, and it's a bit more systematic, that it could work, but people were just sort of, gaming the system, I guess.
Yeah. So when you build a system, it's trust-based, right? But our developers gamed it, right? So if you have a memory leak, it will say, no, this is not a bug, and then it stopped recognizing memory leaks, for example, and that's not good.
That's interesting. Yeah, it's like a code review system where you argue with the system and you can sort of fool it into, that's fine, this code is fine. Or something.
Exactly. Yeah. And also one thing we as we like fast analyzers. So this I'm not marketing, but I think when we build it, then our vision of this of the future ruleless, rules plus unruled static analysis platforms. Core static analysis is really fast. We are 4 times faster than Coverity, for example. Not that Coverity it's a great tool. We love it. We use it too, but we think speed is important, and that's why I said it's next generation. And we would so for us we don't call it out as AI or neural network based. It's a part of the static analysis engine. It combines rules and it combines your own rules. And therefore it is especially the open source, if they really like it, and you could be using Coverity for your DevOps, but I'll also plug this in. And we can also, in fact, there's a funny story, and I won't take the name. So assuming you had a tool from a provider, a security tool, right? We don't do security, and you had reported all issues that the tool has in the rules engine and reported it into your Jira. So our neural network could learn all those rules, and in effect, you would not need the rules anymore. So you could literally reverse engineer, and that is what we didn't realize it till they pulled back, people collaborating with them. They pulled back the support, and I understand why they got nervous. Saying your AI is smart and on our rules, and then you don't need, a customer doesn't need, or you don't pay for it anymore. I'm like, oops, good use case. Maybe that's our cunning plan in the future. And give it for free, right? Just use it, and you make the model better, and in return you get it back. So we are a bit more holistic there.
I mean, it sounds really interesting, the approach, and I think there must be something there. So I totally agree with you're basically saying that in the next few years this will only grow and become more. And I also have the feeling, I mean, we've been using rule-based or typical static analysis for a while now, and I think this taking into account of the context, it seems like one totally missed opportunity, or something we need to start doing is taking into account issues, taking into account commit messages, all that extra information that we have there. At some way to have that at our fingertips would be very useful. So, okay, really, really interesting. Vishal, I think let me check with the questions here from. I had one more that I wanted to check. Have you done any evaluations on accuracy? Because you mentioned that depending on the system, it may be more or less accurate. Have you done some verifications where you've sort of tested it against a baseline or something? Did some sort of verification?
Yes, we've actually done that on Chrome, on large systems, and that's what I said. So for us, it's very simple to test the validation or fine tune it, right? So we take 5 years of commit history, right? We say 5 years of past data. We take the last 3 years, say to train the model, and have it predict bugs, and then we see what bugs it has predicted have they come in the system. It's an easy way to test it, right, in open source, and that's when we see there's massive accuracy. Wow! Cool. So for us, it's very easy to test and validate and fine tune. And there's all the data. That's what I said. Open source is the best community, available for us to learn, to train, and that's what we do. So it's quite accurate.
Okay. Well, I think I will take this back to our development team. We have quite a large code base with a lot of commits in Java and a lot of issues. So I think maybe that could be a good fit.
Happy to learn. Yeah, we are happy to learn. Yeah.
Talk to the developers about that. Cool. Well, thank you a lot, Vishal, for the talk and for your answers to the questions. Where can people follow you, find out more about this topic? What would be good places to go to?
I mean, I have my Twitter account, which is my personal. I know this is not a marketing forum, but
go ahead.
So you can write to us on Embold. So that's a product. It's on embold.io, and if you guys want a trial account, happy to provide it, including the neural network. It's only for Java and C++, but I guess a lot of serious people are doing that development. And if there's any open source community out there, reach out to us. It's the whole platform is free for you. It's on the cloud, and it's really fast. So,
Okay.
so yeah, happy to support.
Yes, super. Well, thank you. We'll probably take you up on that offer. And yeah, again, thank you very much for being here today.
Thank you.
Do you have another session coming up, or let me check? You probably know. No, I think you did the talk, but maybe we'll see you around at the conference afterwards.
Yes, I would love to hang around then.
Okay, then Vishal, thank you very much.
Thank you, Boris. Thank you, everybody. Yeah, bye-bye.
Bye.